videos? No idea. I will post them today, definitely. Okay, so keep in mind, this is what we are doing. We are making an alkene and or alkyne, and then it is reacting with any gas that is in halides. Okay, this can be H2 doesn't actually make sense because what is happening in H2? An H is replaced with an H, but it is a fluorine gas, a chlorine gas, a bromine gas, or an iodine gas. Okay, so we are reacting in presence of some catalyst and some pressure and so on, or water, or an acid, where H is again the halogen group, group 70. Okay, so the bond, the double bond, one of them is broken, and then it is making it available for the entities that we have. Let's say in the case of water, then what we are making is an alcohol because we have a OH. And in the case of bromine gas, we have organic halide, okay? And then what is happening with the hydrocarbon compound, it is from the unsaturated, because you have now a double bond here that makes it unsaturated. You are making it with a single bond, meaning that you are making it saturated. Make sense? It is important when we are working with the addition reaction to watch for isomer. Remember what we said for in terms of isomers, that the molecular formula is the same, but the configuration and the naming, now that we know how to name them, it is different. We'll see some examples. So let's suppose that we have butane, but2N. So but2N. If I'm saying but2N, what this is telling, this ending is telling me, what am I dealing with? Alkane, alkene, or alkyne? Is this one here? Okay, it's alkene. Why? Because it has the same ending, and we are dealing with a double bond. Okay, we are dealing with a double bond. If we are drawing the structural formula of this, so a but2N is reacting with, let's say, bromine. So if we are drawing the structural of it, in which place is the double bonded? Between, starting at which carbon? First, second, third, or fourth? Because we have only 4 here. Which one? 4 doesn't, it cannot start. This number here is telling us that it starts, double bond starts with the second carbon. So we have carbon, and then another carbon, and here we have a double bond, and then we have a third one, and then a fourth one. In terms of the hydrogen distribution, as we have hydrogen, 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 one hydrogen, one hydrogen, and then 3 hydrogens here. Okay, reacting with bromine gas. Now, see what is happening here. This bond, that is this bond here, that is double, it's broken. Okay, let's make it with a different color. This bond here, it's broken, making it possible to have a bonding capacity for carbon 2 and carbon 3, so that the bromine gas is taking the place at. And in this case, what do you have as the end product, as the product of this is something like this. Let's draw the structure. 1 carbon, 2 carbon, 3 carbon, 4 carbon, and then here we have hydrogen, 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 hydrogen that was originally. This is what it was originally. And those two new bonds that are were becoming available are taken by bromine. So now what we have is halide, okay, because we have the Br here, and we have them at 1, 2 di-bromo, and then 1, 2, 3, 4, because it doesn't change, butane. So see now, when, if we are writing it in words, when but2Na is reacting with Br2, then the product is 1 because we have addition. Addition means it's added to 1, 2 dibromobutane. From unsaturated into saturated. Okay, makes sense? So let's see now if it is reacting with HX, where X is a halide. So we'll stick with but2Na just so that we make a point on it. And it is important when it is reacting with HX, where X is a halide, to watch for the isomers. Okay, so we'll see what do I mean by this. Let's suppose that we have again but2Na, and then we have, I will just draw hydrogens here so that it kind of makes sense, and I will draw them with different colors when we are doing the addition, the replacement. And then let's suppose that we have HBr. Okay, so now if this bond is broken, it's making those two bonding capacity available. Then one of them will go to hydrogen and the other one will go to the other bond. Okay, so then what do you have here is C3, 4, and then you have those hydrogen that were originally, so H, 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 and 3 more H's. And you will have one that is coming from the HBr and one that is going here. Okay? Makes sense? However, when we have this, I will draw it again so that we can see it. And then we break this bond here, making available 2 other bonds. Then instead of Br going to the 3rd carbon, now I make it go to the 2nd carbon. So we'll have this H goes here and this Br goes here. Okay, so what we will have here is 4 carbons, single bonded, and the original hydrogens that were here. So hydrogen, hydrogen, that were from the original hydrocarbon. And now here, instead of that, instead of the hydrogen that we had originally, we'll have Br, and here we will have the hydrogen. So when we see it structurally, and when we are naming it may be different, but they are the isomer forms of each other. Okay, make sense? So we explain when we have double bonding. What is happening when we have a triple bond? So between two carbons, we have a triple bond. Okay, good. Now, you have the opportunity that whatever you are reacting, which can be again HOH halide, or an HX where X is halide. Okay, so this can be a Br2, Cl2, an F2, or an I2, and this can be an HBr, HCl, HF, or HI. So those cases, what do you see here is that you can break not only one, but two bonds. Okay, so, and this is totally dependent on if the second part of it, so this one here, is a limited or is excess amount. So if it is limited, then only two spots will be available. Because let's suppose that we have this C, C, and then C, C. Okay, so if one bond is broken here at the double bond, then you'll have two spots available. Okay, but if another bond is broken, then you will have two more spots. Okay, so now if what you are reacting with is limited, then we'll have, at the end of the reaction, we'll have a double bonded carbon chain. If it is excess, then we will have a single bonded carbon chain. Let's see the cases. And again, we have to look for isomers. Let's see the cases. Let's see the first one when it is the limited of this part of the reaction. Okay, either water, H2 halogen gas, or HX where X is the halogen. Okay, let's take a look when it is a limited. So I will stick with this one here because 4. So then we have H, and then 4, H. And it is reacting on this case, let's suppose, with chlorine gas. So we are saying that it is a limited, which means that one of the bonds will be broken, making it possible to have two bonding capacity available, and then one chlorine, because this is chlorine and chlorine here, I'll say and one chlorine is going here, and one chlorine is going here, creating this 1, 2 double bond here, and we have chlorine, and then whatever was that the hydrogen was prior here. Oops, not here. H. So now let's name them. What is this one here? How do we name this one here, this hydrocarbon here? So there are 4 carbons, okay? We'll start numbering it so that the double or triple chain is the first thing that we see. 3, 4. So There are 4, so but, and then we place the name 2, and then what is the ending? What is the ending, guys? I'm asking. Okay, it is reacting with to produce what? What is this one here now that we see here? Again, we have 4 carbons, so but and a double chain. 1, 2, 3, 4. 2. What is the ending? But then, before we do that, let's do this. Before we do this, we have to take into the consideration what? The fact that we have 2 chlorine. So we'll go 2, 3 dichloro, and then but 2-NO, because we are dealing with halide, a derivative of the hydrocarbon. Does it make sense, the naming, guys? So even when you have something in a writing, you should be able to say, 1, what type of reaction is it? And when it is ending with one product, then it is always addition. Okay. And then being able to draw the structural formula of those reactions. Make sense? Okay. So it is important for you to watch for isomers when we are dealing with the HOH. Where is it? Or HF, or HCl, or HBr, or HR, because they can be on 2 different places. This is the case when CO2 is limited. However, when CO2 in this case is excess, then what is happening is that not only two bonding capacities are formed for carbon, but 4 bonding capacities are available. So it is kind of going, when it is excess, it is saying that, okay, everything will break 1 bond for each of them. 1 bond, bum, 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 bum. And then you have excess of CO2. And then CO2 is saying that, okay, then I will break the second bond as well, so that I am, instead of having only 1 broken, so that it is forming something like this. What is doing now this is when you have a limited, but when you have excess, it is saying that, okay, now we have 4 bonding capacities. So here we have 2 to place with, and here we have 2 and 2, 4 bonding capacity. And this is when it is excess. Okay, so 4 spots will be filled. And keep in mind that it is important to look for isomers all the time when we are dealing with this one here. We'll see a case here. So let's suppose that we have but2-wine. So carbon, carbon, and then we have 3 here, carbon, and reacting with HBr as an addition. So 1 bond is broken, then what do you see is 2 free bonding capacity available. So this can be H and this can be Br as a replacement here. And then what is happening after that, the second, since it is excess, the second bond between the 2 carbons is broken, and then you are creating two more bonding capacities. So one hydrogen goes here and one bromine goes here. However, and then what you have here as the is H and Br here and H and Br here. But the Br and H can switch places, and then what you may have is something like this. Br is here and Br is here. Okay, so this is the same compound, like molecular form of the hydrocarbon, but it is an isomer form of it. Because in this case, what you will have is 1, 2, 3, 4, and then you will go 2, 2 dibromo butane. And what you will have here is 1, 2, 3, 4, doesn't really matter which way do you go, 2, 3 dibromo butane. But when you write it as a formula, it is again C4 H 1, 2, 3, 4, 5, 6, 7, 8 H8 Br2 as a compound when you write both of them, and those are isomers. Okay, so pay attention to the naming, because it is important for you to know that you are dealing with a possibility for the halide to be placed in a different places where the free bonding capacity of the carbon is becoming available.